In this video, we will see an example of how to conceptually understand induced EMF, induced current in a closed circuit or a closed coil which is present in an external magnetic field. So let's consider a conducting rod moving at a speed v on a pair of conducting rails. So in this problem we have a conducting rod. So this is a conducting rod. Which is moving with a speed v in that direction, and it is moving on conducting rails. So we have two rails which are horizontal here. This is the rail. This is also part of rail. And so the rod is moving on the rail. And the distance between the rails is L. So essentially that's the length of the rod. And there's a uniform magnetic field B which is present in the region. That's given by the direction is going into the screen, and that's why it's shown as B in. And the rails are stationary, and there is a resistor R that is connected between the rails. This is supposed to be R, which is connected between the rails, and essentially we have a closed circuit made up of materials which conduct charges. Now consider the area enclosed by the moving rod, the rail, and the resistor. So essentially we're talking about this area that you can see is formed here by the rod, the railing, the resistor, and the railing. That's the area. And as the rod moves to the right, the enclosed area increases. And as the enclosed area increases, this is increasing with time, and that's why the flux changes. And flux increases with time. And whenever there's a changing flux, according to Faraday's law of induction, there must be an induced EMF given by this equation. Now, in this problem, the theta is the angle between the rod and the field. And can you guess what is that angle in our given picture? Take some time and think about this. It's the angle between rod or the velocity v vector and the field, which is going into the board or into the screen. And if you are looking at it correctly, the angle is oops, I found a mistake. Angle theta is not between rod and field, so it is that is the angle between the field and the normal. So it's between the field, and this is how we are defined in the definition of flux. You can see that in the previous video, and the normal. And this will come out to be 0 degrees in no problem. It's because the field is into the screen, and the normal is the line which is perpendicular going through like this, through the coil. So it's also going into the screen, so the angle goes to 0. And so this the flux gets simplified to just cos 0 becomes 1, and it's area times the magnetic flux, area times the magnetic field. And if we were trying to calculate the area, we'll do this following. So let's recollect what we had said, that the magnetic flux changes or it increases with time, and an EMF is induced in the sliding conducting rod, and this is the formula for the EMF. So once we have the formula for EMF, let's try to calculate what is N. N is known to be 1 in this problem, and delta phi can be obtained using this formula. In this, the quantity that is changing or that is creating delta here is because the changing area, this is changing. So we want to make sure that this changes as the rod is moving, because the loop is becoming bigger and bigger. And we can calculate the change in area here. This is the change in area. And once you have the change in area, you can get the change in the flux. And once you have the change in flux, you can get delta phi. This essentially becomes this one. The numerator is B times delta A times 1, because the angle was 0 degrees, divided by delta T. And delta A is this value. Put delta A there, and you will get a velocity coming up there. It comes up in the calculation, and finally you will get the induced EMF to be given by this formula. This is induced EMF. This is a last simplified formula, and this is how you get the induced current. You get the induced EMF divided by the resistance. Here I have not shown you the derivation of the induced EMF, but I gave you the final equation. But essentially, by doing this calculation, you get this value. Let us do a problem of calculating induced EMF when a bar magnet is brought closer to a coil. And let's assume for now, even though we see like 3 coils here, we'll just say N equals to 1. Just a single coil for simplicity. And the problem is, calculate the magnitude of induced EMF when the magnet in the figure is thrust into the coil. The single loop coil, so that's N equals to 1, has a radius, so that's your radius. This will be helpful in getting the area of the coil, and the average value of the B cos theta term. So they're giving you the average value of B cos theta term instead of giving you average of B. It's just because the problem is set like that. It's just they gave B cos theta instead of B, and they're saying B cos theta changes from this value to this value and in this much time. So this is delta T, and using this you can get delta B cos theta, change in B cos theta, and that's delta T. So induced EMF using the Faraday's law of induction is this. Here note that we are just calculating the magnitude because the question is asking for magnitude. And N is 1, delta T is given, and change in flux is this. In this, A is a constant because the loop is not changing in area. Loop's radius is fixed. Only the magnet is moving. And once you calculate delta phi, we are able to get delta phi using the formula. You just take delta B cos theta, which is subtraction. This is delta B cos theta, and multiply it with the area. So this is essentially delta B cos theta times area, pi r square. that's change in flux, and change in flux divided by change in time will help us calculating the EMF, and that's how you get the EMF, which is shown in our calculation here, and it comes out to be about 22.6 millivolts. And of course the picture gives you the direction of the currents and the induced fields B coil. We discussed these directions before using the Lenz's law concept.